Okay, so what I want to do this time is take the idea of a group, something that every mathematician knows and loves, and sort of muck around with the definition so that the definition becomes categorical, so that we talk about some object in some category with some properties, so that we can then lift up that definition and plonk it in other categories. Now, there's going to be certain subtleties in that taking up and plonking into other categories, because we're going to start in the category of sets, and it's not entirely obvious what properties we're going to need when we go to things like Hopf algebras and monoidal categories, which is where we want to go. So don't worry about that at the moment. This talk is just going to be about groups. So what's a group? So a group, as you well know, so a group is going to be a set G with some stuff. So what sort of things does a group have? So firstly, it has a product, so there's a notion of product of two elements. So if we have a pair of elements A and B in G, then we have their product AB in G, and so I guess you can put a dot there if you want to. You can just use juxtaposition, so let's just write it as juxtaposition. We have the inverse, so if we have A in G, then we have the inverse, which is A inverse in G, and we also have this special element E in G, which is the unit, and this data has to satisfy various properties. So in particular, precisely the properties that it has to satisfy is firstly, in no particular order, but firstly we have associativity, which says that if you take A, B and C, you multiply B and C together, then that's the same as doing the other way around. So A, B, C, doing A times B first, and then C. So then we have the, let's go for the inverse, let's do the unit one now. So it's the inverse one that's going to cause us a bit of trouble later. So the unit axiom says that E times A is equal to A, which is equal to A E. And then the inverse says that A inverse times A is equal to E, which is the same as A times A inverse. So, of course, all this is completely standard stuff. But what we want to do, as I was trying to explain in a waffly sort of way, is take this idea and express it in a categorical fashion, so we could talk about groups in other categories than sets. So the first problem here is that we're talking about elements of G. Now G is an object in our category set, and for categorical definition, we don't want any elements kicking around. I mean, we don't want to look at any internal structure of G. We want to think of G as sitting inside this category of sets and use that kind of level of construction and not talk about the stuff inside G. So firstly, we can rephrase the product in a different way. So let's just rephrase all this. So I'll start at the bottom so let's replace the idea of the product. So we're going to replace that with something a bit more categorical in notion, in nature, which is we have the multiplication. There goes the border over, which is supposed to be a map mu from G cross G. So suppose things in G, you think about it as into G, where this is the product in sets, the Cartesian product. Then we have inverses, so similarly, we have that gamma from G to G, and we have the unit. So how do we express the unit? Well, we'll call it E again, and so E is going to be a morphism from the terminal set, well, a terminal set, so a set with one object into G. So that's what we've got there. So there we're not talking about elements anymore, we're just talking about maps, which is definitely more categorical, and we just have to express our three axioms in a better fashion now as well. So let's scope of associativity. So if I just rewrote this, this is, so what I did was I did mu b comma c, magic board rubber, mu a, mu b comma c is equal to mu of a comma b comma c. So that was the associativity, or a slightly better way to write the same thing is, so what am I doing? So I'm doing mu, and then I'm composing with, I guess I'm doing, so let me just write it out and then explain. So if I start with three elements A, B and C, then I apply mu to the first two, the last two, find the identity to the first one, so I'll get that stuff, and then I just apply mu to the whole thing. So, and similarly on the other side, this is mu composed with mu cross ID of A, B, C. So I want this to be true for all elements A, B and C, so I can just say that my associativity is this equality of maps. So I'm not talking about elements anymore, this is equality of maps. So if you want to think about things in terms of commutative diagrams, which you might prefer to do, then this is just express this as G cross G cross G to G cross G down to G cross G, where we have identity cross mu, mu cross the identity, mu, mu. So this axiom is just expressing this. So let's just go with this. Top. The unit, I can just replace this by saying that mu composed with E plus the identity is equal to the identity, which is equal to mu identity plus E. And the inverse is, well, just have to be slightly careful here. So if I had mu of A comma A inverse, let's just do one of them. I want that to be equal to the unit element E. So this is mu of, so I'm mu, here I've done the identity cross gamma of A comma A. So I'm just taking the inverse of the second one, nothing to the first one, and then just multiplying them together. So this is supposed to be equal to the element E. So this is mu composed with identity cross gamma and composed with delta of A. And how can I write E as something in terms of A? Well, I'll just write it down and explain it in a second. So I take A, I send it to the one object set with eta, and I do E on that. So eta is the map from G to the terminal object, so this is terminal, so there's a unique such thing. So here I've got some equality of maps. I haven't told you what delta is yet. So delta was supposed to be, delta was the map from G to G cross G, which just goes from an element A, it sends it to A. Okay. So this is the diagonal, the so-called diagonal map. Okay, so we'll explain where this thing comes from in a categorical sense, why we have this nice thing in this setting a bit later. But we'll just, it's just an obvious map that we've got. So now this is supposed to be true for all elements A, so I can just express this as the equality of these two maps from G to G. So I can just remove all this chaff here. And I'm just about out of time. So what I've done now is I've just rephrased the idea of a group in terms of its objects and things as an object in a category. So it's an object in the category of sets with three maps and some equalities between various maps. So next time we'll do some other things with this. Right, so this time I'd like to say a little bit more about the idea of a group as a thing inside set, the category of sets. So, first a few notational points. So last time I just kind of lost it somehow. I should have called this thing eta. The unit I should have called E. Last time I called that E. I should really, can't see that, but probably a good thing. I called this E last time and it should be called eta. And I called something eta which should really have been called epsilon. So epsilon is supposed to be this sort of terminal map from any set to one object set, the unique such thing called epsilon. So another comment I should make is about this unit axiom. So if you stare at it carefully, then you see there's a bit of a type, an error of type checking. So this is supposed to be the identity. That's a bit harder. Identity on G and the identity on G. They seem to go from different things. So if I just write this out as a commutative diagram, it might become a little more clearer. So what we have is. So we have this isomorphism. G is isomorphic to G cross a point. This is just the thing that you have in sets. It's the obvious isomorphism, and it's from there that we can then apply. Oh, we'll go this side. We do the identity on G. We'll do eta. So we go. Not sure which way around I'm going this square. So we're going G cross star to G cross G, and then we can do mu, and that's just the identity. So this little map here is sort of hidden in this notation, so I should just put that in the notation. So where this is the unit map. Okay, so the next thing I want to comment on is delta. So this is an important bit of structure of the category of sets. Whenever you have a set, you have the diagonal map into the set cross itself, just by the fact that the Cartesian product we're using here is the product in the categorical sense. So what is a product in the categorical sense? To remind you about that. So if we have sort of the categorical motion of the product, categorical product. So if we have a pair of objects, what am I going to call the objects? Let's call them A and B. We have A cross B is a product if it comes equipped with two maps, projection to A and projection to B, pi B if we want to call them, give them names, we'll call them pi A and pi B, with the following universal property. So the universal property is that if we have maps, let's call it little a's as elements of the group. So let's call them little map alpha here from X to A, and we have a map beta from X to B. If we have two such of those, then we have a unique map from X down to, this is supposed to be unique, A cross B, such that if we compose that with either projection, oh, I'm sure I've got a bit wonky here, but never mind. If we compose it with either of the projections, then we get the two maps that we first thought of. So given two such maps, we have this. So this is the fact that we have a categorical product. So cross, the Cartesian product is the product in the categorical sense. And so what is delta? So delta is just coming from the kind of the silliest thing you could possibly think of, which is, so if we have, we just take these two maps, alpha and beta, we just take alpha just to be the identity from A to A, and beta to be the identity from A to A, then we have this unique map into A cross A, such that we get the identity. And it's this unique map of this property which is called delta. So delta comes out, the diagonal map delta comes out of the structure of the category of set. So this is embedded in the category of set. So I don't have to refer to elements here, which we don't want to do. Don't have to refer to the elements. I just use the universal property of the categorical product to do that. Okay. So that's going to be important in a minute. So what else do I want to say? So another important thing to say is, if we look at these two things, the associativity and the unit axioms, and I get rid of the, oops, I should have ordered this slightly better. We're going to take these two bits of data, satisfying these two bits of axioms as they are. Then what I can do is I can see that this is just the definition of a monoid. So if I just taking associativity and unit means that a group is a monoid in set. So remember, a monoid objects or monoids can be defined in any monoidal category. So I guess what I'm saying here is sets is a monoidal category. So this is a monoidal category when it is equipped with the Cartesian product, and the unit object inside that monoidal category is just this terminal set, the one element set. But you knew that already. You knew the group is just a monoid with some other stuff, which is just the inverse, satisfying the inverse property. Right, so we know that a group is a monoid. What you might not know, however, is that every set is a comonoid. So you take any set, any object in the category of sets, and it turns out it's a comonoid. So what's a comonoid? So a comonoid is just the same as a monoid, except it switched everything round. I mean, that's a bit of a silly way of saying it, but that's really what it is. So a comonoid is something. So a comonoid is something with a co-multiplication. So this is S is going to be something with a co-multiplication. Well, not delta, but let's just call it thick delta, just not to confuse it with delta there. So it's from S. So this is a comonoid in sets. Obviously, you can define it in any monoidal category. You just switch everything around. So that's the product going the other way, and we've got a co-unit, which we call epsilon. Let's just call it sort of thick epsilon for a minute, going from S. So it goes to the unit object, satisfying sort of associativity and unit turnaround, satisfying co-associativity and co-unit, which are just, if you draw the commutative diagrams for these two axioms, then you just switch everything around. The multiplication becomes a co-multiplication, and the unit becomes the co-unit. So the point I want to make here is that every object in set is a comonoid in a unique way. So there is only one possible comonoid structure you can put on it, and it is automatically there. And the point is you use exactly these two structure maps. So so I should just write that. I'm just about out of time. I should just write this down. So let me just leave that chap up there. Sets as a monoidal category. So the fact that the cross, just about out of time, is a categorical product means there exists a unique comonoid structure on every set S, and it's given precisely by if I replace G by S. Okay, so that's a good place to stop. Okay, so what we saw last time was how we take the naive definition of a group and sort of give it a categorical flavour. So what is a group? Well, the way we've decided to describe it is it's an object in the category of sets, so it's a set together with certain morphisms. So we've got the multiplication, the identity, which we've, instead of thinking of this as an element of the group, it's now a morphism from the terminal object in the category of sets to our group, and inverse, which are called gamma. So we've got three morphisms, we've got an object, three morphisms, and satisfying certain axioms, the usual axioms, so associativity, unit, and inverse. So if we just kind of step back a second, if we remove the inverse morphism and the inverse axiom, then what we've got is something you can find in any monoidal category, which is a monoid. So something satisfied with a product and a unit, and satisfying the associativity and unit axioms, that's just a monoid. And so we can happily define that in any monoidal category, as we'll see in a bit. But what we have here is this inverse is going to cause us a slight amount of problems, because to actually define the axiom for the inverse, what we need is these two extra bits of data, which are delta and epsilon. So these come for free in the category of sets because, as I explained, we've got the categorical product as our tensor product. So cross is a product in the categorical sense, so we automatically get this diagonal map for free. This satisfies a certain universal property, and we get this map to the terminal object, this sort of unique thing there. And so with this bit of data we can then define the inverses. So this definition is not going to work in general for monoidal categories, but it is going to work for Cartesian categories. That's categories, monoidal categories, whose monoidal product is the categorical product. So let's just, so what I'm saying is we can just take this definition now. If you give me a Cartesian category, then we can just take this definition and say what it means to have a group object in such a thing. So let me just write down the first 5 Cartesian categories that spring to mind. Okay, so which ones can you think of? So I can think of, well, the one I've written down there, which is the category of sets. I can think of top, the category of topological spaces. So the product is just the usual Cartesian products of spaces. I can think of smooth manifolds. I can also, what's another one? Oh, the category of groups and the category of categories. Now, in each of these cases, I can tell you what it means to be a group object. So it's just I'm just going to replace sets by whatever the category is. Here, these are Cartesian categories, so we automatically get for free these two morphisms, and we can understand what a group object is. So what is it? So what's a group object in set? Well, I've already told you what that is. It's an unpleasant little line. So a group object in here is just a group. A group object in topological spaces, so that just comes down to a topological group. So you can just, so it's just a topological space with a product such that the product, and an inverse and a unit such that all the morphisms are continuous. So it's a topological group. Do the same thing in the category of manifolds. Smooth manifolds, we get a Lie group. So that's sort of the obvious one. So it's slightly more interesting what goes on with the category of groups. A group object in the category of groups. Well, what's that going to turn out to be? So it's clearly going to be a group with possibly some more stuff. So when you actually sit down and figure it out, rather bizarrely, it isn't a group with extra stuff. It's sort of a group with less stuff almost. But well, anyway, I'll explain what I mean by this. So turns out it's just an abelian group. So it's got to be a group with a product from the Cartesian product of the group to itself, which is a group homomorphism between these two things. And it turns out that just means this has to be the product in the group, and that has to be commutative. So we end up with an abelian group. So I'll leave you to work out the details of that. So a category of categories, a group object in there, is something which arises in various contexts. I guess I'll just call it a cross module. It's also a categorical, it's also a category in a category of groups, but that's not of much interest to us at the moment. It's just a different example of a group object in a Cartesian category. So these are nice Cartesian categories, but we often want to consider things that look like groups in monoidal categories which aren't Cartesian. And the big problem is we don't have this stuff around. I'll explain a little bit why we want to look at these next time, but we don't have these two things around, so we have to sort of work around not having these, and we'll see how we do that next time. So what I'd like to do this time is just explain an example of a monoidal category which isn't Cartesian. So let me get rid of this now. So the simplest example of a monoidal category which isn't Cartesian is one which is very familiar to many of you, I suspect. It's just a category of vector spaces. So just for simplicity, I'm going to take vect to be the category of vector spaces, finite dimensional vector spaces, with the complex numbers. So we have a tensor product. So we have a tensor product, and we have the unit object, which will turn out just to be the complex numbers. So what is the tensor product? So the crunch is what is how is this thing defined? So if we have two finite dimensional vector spaces V and W, we define the tensor product in the following way. So what do? We take all formal linear combinations of a vector in V tensored with together with a vector in W. So let's just so we're going to take some summation, some finite summation of some linear multiple, so that's just a scalar of Vt times Wt. So that's just a symbol, something in V and something in W, and just a scalar. So that's in C, that's in V, that's in W. And modulo, so we just take the set of those, modulo certain relations, and the relations just say that if we have alpha 1 times V1 plus alpha 2 times V2 tensored with W, that is equivalent to alpha 1 V1 tensor W plus alpha 2 V2 tensor W. And the one the other way around, plus V tensor linear combinations of W's is equivalent to V tensor whatever plus V tensor whatever. That's just the symmetric one the other way around, which I won't write down. So that's the definition. Now what you can kind of see very quickly is how to get a basis of V tensor W. So if suppose we had a basis Vi for V, and let's say Wj is a basis for W, then Vi tensor Wj is a basis. Oh, I could have cunningly written it down, couldn't I? Then we get that Vi tensor Wj. You can quite easily see from the definition there, just a couple of lines of calculation, is a basis for V tensor W. So, what's the sort of corollary of that? Well, just say what I've got to say very quickly. So the point is that the dimension of V tensor W is equal to the dimension of V times the dimension of W. But that's not the same as the Cartesian product. So the Cartesian product, or the direct sum, satisfies V cross W. I mean, the dimension is is the sum. So the corollary is that the tensor product is not the Cartesian product. So this is a category, it's a monoidal category which is not Cartesian. So we'll say more about this next time. Okay, so what we've done so far is seen how to define a group object in a tensor category where the tensor product is Cartesian, is the categorical product. And I've just shown you a good example of a tensor category, monoidal category if you like, in which the tensor product is not the categorical product. And we want to be able to define a notion of a group object in some appropriate sense in such a thing. Well, you could ask why. There are several reasons. I mean, you often get functors from categories like the category of sets into linear categories, for instance, like the category of vector spaces. So off the top of my head, you know, I think you've got, if you start with something like a topological group, and then you take the cohomology of that, then that's going to be some sort of tensor functor from some Cartesian category, Cartesian monoidal category into a non-Cartesian category, and you want to look at what the image of that is, and it should be some sort of group object. Or another example is you just take the group algebra of a finite group, say. So you start with a finite group, so just something in set, you take its group algebra, so just the vector space spanned by the elements in that group, and that ends up in the category of vector spaces. But essentially all the information about the group is contained in this group algebra. So if you're doing representation theory, then you can just look at this manifestation of the group in this linear category instead, which is not Cartesian. So that's sort of why we want some decent definition inside things which are not Cartesian. So let me just expand a little on the Cartesian situation. So here, so if we have mess of this chalk, if we have a category monoidal category C. Let me write the monoidal product as a cross, just to emphasise the fact that the tensor product is a categorical product, where cross is the categorical product. Then let me just revisit the statement I made at the end of a previous lecture, which was the case where we had set and Cartesian product and the so set, Cartesian product, and the one object set there. Then every object in C X in C is a comonoid in a unique way, and every morphism is a comonoid now. Let me just remind you a little bit what I mean by a comonoid. So a comonoid, so what we have is a map delta from X to X cross X, sometimes called the diagonal or co-product. And an epsilon, let me just write it a little strangely just to distinguish it from the things I've written down there, for the moment, goes to the unit object. The unit object for the tensor product, which is going to be the terminal object in the category. So this is the unit. And so these are just the things you get in a monoid but switched round, and consequently they have to satisfy the switched round axiom, so that has to be co-associative. So just write down the associativity commuting square for a product and reverse all the arrows. Get this. So what am I saying here? So every object X is a comonoid, so we have such a things, but it's in a unique way. Now, because the category is Cartesian, because we've got the categorical product, I proved earlier that every object we have these things, and in fact that's the only way you can make an object in such a category into a comonoid. So although I wrote these in a funny way, in fact they were the ones that they were supposed to be. So this is in fact the diagonal. This is the diagonal map. So the thing that comes from the universal property of the Cartesian product, of the categorical product, and this is just the unique sort of map to the terminal object. So this is what's going on. This is sort of what's special somehow about Cartesian categories, Cartesian tensor categories, rather than ordinary run-of-the-mill kind of tensor categories. And we're using this fundamentally in the definition of a group object, although it's sort of under the carpet a little bit. So to do group objects in non-Cartesian tensor categories, we're going to have to put this in by hand. Okay, so I guess I will just I'll just write down the definition of a Hopf algebra. So it's worth making a terminological comment at this point. So the notion of a monoid in a category versus an algebra in a category. So I guess there's some variation in usage. So often category theorists will call things monoids, which say quantum topologists or whoever might call algebra objects. So it's just because, you know, what is your canonical example of a monoidal category? So if you sort of take it to be set, then a set with a associative multiplication and a unit is called a monoid. But if you do the same thing in the category of vector spaces, you take a vector space with an associative product on it, you get an algebra. So sometimes you sort of generalize this to a sort of a general category. You would either have a monoid, you can either call it a monoid or an algebra object. So if I use these interchangeably, they mean the same thing, you know, or similarly a co-monoid or a co-algebra object. So it's not confusion. So that's just a terminological issue. So it talks about Hopf algebra, which is going to really be a sort of a group object in a sort of in a general category. So it's going to be this plus some axioms. So what is it going to be? So it's going to be, well, it's going to be a monoid. So a group is a monoid or an algebra object, whichever terminology you want to use. It's also going to be a co-monoid or co-algebra. Now this, the multiplication and the units of the multiplication are going to be co-monoid maps or co-algebra maps, and it's going to have an inverse. So that's basically what a Hopf algebra is. So I guess I will write down the details next time. So maybe I'll just write down so Hopf algebra. So this is going to be an algebra. Well, it's going to be a co-algebra and an algebra with structure maps being structure maps. Co-algebra maps plus inverse. So it's that data there basically. So I'll go into the details next time. Okay, now I just want to cut to the chase and tell you what a Hopf algebra really is. So remember, we're trying to model a group object in a more general monoidal category than a Cartesian monoidal category. So a category in which the tensor product isn't necessarily the categorical product. So that's going to cause us a few problems, as we've seen, but we can get over that with the definition of a Hopf algebra. So that's precisely what a Hopf algebra is going to do for us. So a Hopf algebra is going to be something in a monoidal category. We're going to have braided monoidal category. Don't worry if you don't know what that is yet. We'll come to that. But so the example you should be thinking of here is either the set with the Cartesian product, which is and this is just going to give us the definition of a group, or the category of vector spaces with the usual tensor product of vector spaces. Okay, so what I said before was that we needed, well, a group is going to have a multiplication and a unit, but in a Cartesian monoidal category, we automatically have that every object is a comonoid in a unique way. So we're going to have to put this in by hand. We're going to have to put the delta in by hand because in an arbitrary monoidal category we're not going to get that. So we're going to have to put that in by hand here. And these maps are going to have to be, we're going to have to put this in by hand again, these are actually going to have to be maps of coalgebras. I'll explain what that means in a minute, and then we're going to have to throw in our inverse. So let me just start by using a bit of string diagram notation, if you remember what the string diagram notation is like for monoidal categories. So let's just, well, firstly I'll just remind you what this is. So if we have something, we have a map, something like, it's a Greek letter, theta. So theta from, let's say, A tends to B to H tends to G. We'll just notate that as something as follows. Can you see the blue?
Just press a bit harder.
Right. Okay, well, it's not going to be important. Let's try to do it right then. Theta is going to be from A tends to B to, let's say, G tends to H. So we would just write that as some A, B, with the tensor sort of understood between them, going into something having some blob called theta, and then we have GH at the top. So what we have here, well, let's write our H's always in red. So we've got the co-product is going to be something which we draw like that. It goes from an H, everything's going to be labelled with H's here, H to H tends to H. The co-unit is going to be something from H, goes from H, but then it sort of stops abruptly and then goes to our monoidal unit. And as you know, as you remember very well, where we don't draw the monoidal unit, we just indicate it by absence. And then we have the product goes from H tends to H to H. We have the unit goes from nothing, absolutely nothing, to H. And we've got the antipode. So we draw the antipode as just a line with a little thing in. So that's supposed to be like a twist. So of course I could just put these in, might be helpful if I just put these in boxes for now. So you see that. Okay, so these have to satisfy the axioms. This has to be a co-algebra or a co-monoid, if that's the language you prefer, co-monoid, co-algebra. So this has to be co-associative and this has to be a unit. So should I write that down? I guess I'll just write that down very quickly. So co-associativity, remember, is so it's just associativity turned upside down. It's, you can write that down in terms of commutative diagrams if you prefer, but it's just a simple string diagram notation for it. You just do the co-unit, and you can either then apply the co-unit to the thing you get on the left or the thing you get on the right, and that's supposed to be the same. So we have co-associativity and we have co-unitness, which just says that if we do the co-multiplication and then we apply the unit to either side, that's the same as doing nothing, which is the same as doing on the other side. So we did the co-unit and then applied the unit on the left instead. Okay, so that's just the co-algebra conditions. The fact that we have an algebra here are just the fact that mu and eta satisfy the usual conditions for an algebra. So it's exactly the same. That's equal to that. That's associativity now. Associativity, not co-associativity. And we have the unit condition. So if we get the unit, we multiply anything by the unit. It's just the same as doing nothing on either side. Ooh, to the side there. Okay. So now we get to the hard bit, or the slightly confusing bit here. So we need this to be compatible, these algebra and co-algebra things to be compatible, even before we get to looking at the inverses. So this is where the braidedness comes in. So what does compatible mean? So compatible means that these algebra structure maps have to be co-algebra morphisms of co-algebras. So in order to do that, you find myself some space. So we need that mu and eta are co-algebra maps. So we need. So what does that? Well, we just have to think what that means for a second. So in particular, we need that this is a co-algebra. So we need H tensor H is a co-algebra. Well, here we use the following fact. I mean, if we just have two co-algebras, it's slightly confusing that we've got two copies of H. It becomes less confusing if we have two different things. So suppose that H and K are co-algebras, then H tensor K is a co-algebra if C is braided. So braided, well, let me just explain how we do this. So what we want a co-product on here, but we have a co-product on H and we have a co-product on K. So we can just apply those. So if we just go H tensor K, and we apply the co-product there and the co-product there, we get H tensor H, H tensor H, tensor H. Oops. Ooh. K tensor K. Now what we wanted was this, for this to be a co-algebra, we wanted it to go to this tensor itself, but the order's mucked up. So we want to be able to switch these two round, and that it's exactly this which you get in a braided monoidal category. So using the braiding. Okay, so provided we're in a braided monoidal category, then we just take H to be equal to K here. Then this automatically becomes a co-algebra. And you can then write down what it means for this to be a co-algebra map. Okay, and I'll give you a chance to figure out what that means for yourself. Right, so hopefully you've done the homework, but if you haven't, then I'll go through it now for you. So what we were seeing here was how to define a co-algebra structure on a tensor product of two co-algebras. So I should show you how to do that string diagrammatically first. So I'll try and do this with two colours. So we had H. We start with H and H is red, isn't it? So we start with H in red and K in white. And the idea is we want to go from red white to red white red white. So how do we do that? Red white red white. So what we do, of course, is the only thing we can do, because we've got a co-algebra, is double the reds, double the whites, and the fact we're in a braided monoidal category, we can go from the red white to white red, so we can pass the red over the white. So this is then the co-product on here. So here we're using, this is the braiding, so that's the braiding, and the braiding, a braiding in a monoidal category is a natural transformation tau AB from B 10 to A to A 10 to B, which is sort of natural in some suitable sense. So just a symmetry, just for instance, in the category of vector spaces, you've got this isomorphism between V tends to W and W tends to V, which is just got by going from V tends to W, you just got a vector V and a vector W, and you just switch the order around. Okay, so that's just a simple one. But they can be more complicated, so this sort of generalizes the idea of just a symmetry in a category. Anyway, so the point was, what was the point? So where on earth was I? So if we think back, we were needing to show that these are co-algebra maps. So mu and eta had to be co-algebra maps. So if we do delta on that, and then do mu, or we do mu on that and then delta, sorry, the other way around, delta on that, then mu, or mu on that and then delta, we should get the same thing. So I can now write this down. We had that we needed to show that, we needed to state the condition that mu is a co-algebra map. So if I do delta and then mu, it's the same as doing mu and delta, essentially. So if I just write that down, so we're saying that delta composed with mu is mu tends to mu with delta. So what I really want to do is just write that down in terms of string diagrams. So if I do mu and then I do delta, that has to be equal to doing delta. Oh, see, I got it all the way around again, didn't I? So that should be delta. Well, that's delta on H. So what was delta on H? Sorry, delta on H tends to H. Oh, I'm in a good one, am I? Right, so delta on H tends to H, as we saw, was we do the delta of the individual things and then we use the braiding. So that was delta on H tends to H, and then we just do two copies of the product. So we have this little diagram, which I can then neaten up a bit, because you can't see it very well. Press very, very hard this time. Blah, blah, blah. There we go. Very, very hard. Looks like I'm destined not to draw that one very well. Okay, so that was mu being compatible with delta, but of course it also has to be compatible with epsilon, but that just says that if we do epsilon, mu followed by epsilon is the same as doing epsilon, so we can write that mu followed by epsilon is just equal to doing epsilon first on H tends to H. And I didn't tell you what epsilon on H tends to H was, it was just epsilon tends to epsilon. So we have that one. So these two axioms are expressing the fact that mu is now a co-algebra map, and we can express the fact that eta is also a co-algebra map, so that gives us another two axioms which we can write down quite simply, as well as that one turned upside down. That's true. So if we go from nothing by epsilon, and then you do Q product, then that's just the same as doing 2 copies of epsilon, and sorry, not epsilon, that's eta of course, isn't it? Right, okay, and plus one other, which I'll just use as a little exercise to find the other axiom, which is saying the compatibility that eta behaves well with respect to the co-unit. So I'll leave you to think about that. And the last thing then, so before I do this, there seems to be some asymmetry here. So it looks like this co-algebra structure is sort of more primeval than the algebra structure. Now we saw that was the case in in a Cartesian monoidal category, which is why I wrote it like this. In fact, I could have written it the other way around, quite happily, that we had an algebra together with a compatible co-algebra structure. So in fact, if you write down the fact that these are algebra maps, then bingo, you get exactly the same things out. So although I wrote it down asymmetrically, in fact it is symmetric. So you can find that other axiom there. And then all I need to do is express the antipode, which was the remaining axiom we have to find, which was as follows. Remember, you take G, you double it, you take an element G, you double it, you apply the antipode to the inverse to one side, and then you multiply them together, and you should get the unit back. So that's quite easy to write down. So we do delta, and then we just apply the inverse to one side. So I'll write it like that, and then I multiply these two together, and I get some element, and that element is supposed to be the unit element. But how do I get that? Well, remember that was supposed to be saying that if I do epsilon, and then I do eta, so I do the co-unit, then the unit. This picks out the unit in the group for me, and so it says that has to equal that. So that is this is the antipode axiom. Well, of course, there's 2 versions of it. Remember, G inverse is equal to the identity, but also G inverse G is also the identity. So we have another version where I get rid of that, and I write it on the other side. So there's 2 versions. And so that, therefore, is the list of axioms for the Hopf algebra. Thank you.